Hello, good afternoon. So today I'm going to discuss about the optimization of the process using the Taguchi design of experiment in the R software. So I'm Shantanu Tamuri from the Department of Veterinary Biochemistry in Assam Agricultural University. So let's go ahead. So now there are lot many videos that has given the details about the Taguchi's design of experiment. So I will not go in details because I will only demonstrate how to perform the Taguchi's design of experiment in the R software. So it is, as you know, that it is a fractional factorial design, and it can be carried out in the less number of experiments as compared to the full factorial design. So for this Taguchi's design of experiment in the R, in order to carry out this, you require these packages. So first one is the dplyr package. You need to install in the R software, then tidyr, devtools, and qualityTools. So qualityTool is the main software, main package that carries out the this Taguchi's design of experiment. Okay, now the qualityTools package, this particular package is not available in the CRAN. So for this you will have to install first the devtools, and then you will have to install it from the GitHub. So this is the way. Just first of all you install the devtools package, then using the library command you load the devtools package in the R software, and then you carry out this particular command. So thereafter the qualityTools will get installed. This cannot be installed using the install.packages. It will have to be installed from the GitHub. Thereafter we can proceed further. So now here in this tutorial I will show you one example experiment. So in this particular example experiment I am having 7 factors with 2 levels each. So now I need to carry out the Taguchi's design of experiment as well as the analysis. So now this particular experiment, it will come under which array of the Taguchi's design, this we'll have to see. So these are the different arrays of the Taguchi's design. Say L4 it is for 3 2-level factors, then L82 for 7 2-level factors, then 93 for 4 3-level factors. As such, these are the different arrays that are categorized in the this Taguchi's design. So this is then the rest of the things, and these are the different design of experiments under Taguchi. Okay, now in our case, if we see that we have got 7 2-level factors. So in that case, this will be the design of experiment. In our case, in this particular example, this will be the most appropriate design of experiment. So now we'll have to proceed with the R software to carry out this analysis. So we have 7 factors with 2 levels. Now in order to find out which DOE it falls in, we go to the R software. So here this is the L82, this is the we have already seen. Now we'll go to the R software. So this is the R software. So first of all we will require tidyr and dplyr. So using these 3 commands we can load the packages. Click the run here. Okay, it has been loaded. Now next is I need to make the design. So this is the code Taguchi design, and then design is equal to L8_2. So this L8_2, it has to be written in the quotations under this semicolons. Okay, then followed by randomize is equal to F. That means randomize is false. So I don't want randomization. And then replicates. That means for each experiment there will be 4 replicates. So if I just run this code, I run this, and then I see. So this is the design of experiment that has been made by the R software. So I'll just copy this design in the Excel sheet. So for this I will use this particular command, that is that is the write.csv, then TDO. So TDO is just the Taguchi design, that's why I just use this vector, then this clipboard and the root name. Just if I just run this command and this code, now this particular design has been entered into, it has entered into the clipboard. Thereafter I need to go to the Excel sheet. So this is the Excel sheet. So I just, because the design is already copied, now I need to paste it. So if I click paste here, so it gets pasted in this way. So now to have a put it properly in the Excel, now next is I need to go to the data. Then in data I need to click the text to columns. After that just click next, and then here select the comma. After that finish. So now what you can see here, the design has been nicely, it has been pasted into the Excel sheet. It has been pasted. So these are the A, B, C, D, E, F, G. So these are the 7 factors, and this Y stands for the response. I mean, what is the result? Result will come over here. And then you can see that A, under A you have 1, then again B1, C1, D1. So these are 1 indicates it is the low level of the factor. Then again next is also say A is 1, B is 1, C is 1, but D is 2, E is also 2, F2, G2. So 2 stands for the higher level of the factor. So this is the way we'll have to, this is the design of experiment that has been made. Okay, then you will have to carry out the experiment. Okay, and after experiment, whatever value you get here, so what is this NA written over here, you will have to delete this NA, and then here you will have to enter the result. Okay, so this is the result I have already obtained. Now this result, after obtaining, I have put it under the Y. Okay, now for analysis we'll have to go back to the R software. Okay, sorry, now for analysis we'll have to copy this completely. We just copy it. So while copying, you have to remember that you have to copy headers also, as well as all the values. Just take care that no value should be left while selecting. Then copy. So after copying, go to the R software. Okay, now so this is the code for pasting the stuff that we have copied. Click run here. Okay, and then the yield means in this case this one is the Y under Y, whatever it is yield. So I just name it as yield. Run. Thereafter next is I need to describe the response. To describe the response column I need this particular code. Okay, and then the next is now I need to go for the signal to noise ratio. This is the signal to noise ratio plot. So for this, the first of all I need to type the TDO. So TDO, you remember, this is the design that was made by the software. So TDO I have written here, then type is equal to larger. So that means here, you know that in case of Taguchi's design, you have 2 types of signal plot. One is the larger is better, and one is smaller is better. So in this example I am taking larger is better. If it is smaller, so this instead of larger you'll have to write here smaller, but it has to be written inside the quotation. Okay, then points is equal to true, so you'll have to write, if it is false, then what will happen, this points will not appear. Then color I'm putting as black, so one line will be there, so this line color will be black.
and PCH stands for the shape of the points, and LWD stands for the width of the line, and LTY stands for the line type. So I have given here 5 and 1 is a line type. Okay, then YLab. So YLab stands for the label of the y-axis. So I'm putting here mean of ascent ratio of yield. So you can write here anything that you wish inside because it's a label only. Now I run this code. So now this is the signal to noise ratio plot I have obtained. So same plot I have put it in the PowerPoint also. So this is the signal to noise ratio plot that we have obtained from the R software. So what you can see is that in the factor A, okay, here the line is going like this. For factor A, this is level 1, this is level 2. So it means level 2 will give better result. That's what it is showing. Then factor B, it is again in the factor B also level 2 is giving better result. But in case of C, what you can see, the factor 1 is giving better result because the line is towards the factor 1. But here the line is tilting towards factor 2. So for D, it is a factor 2 that should be chosen for the optimized response. Now for E, there is not much deviation, but still here the factor 1 is more important. Now the F, what you can see is that here also the line is deviating towards factor 2. Then G, in the G, what you see, the line is deviating towards upward towards the factor 1. So for A, the line is deviating towards factor 2, and for B, the line is deviating towards factor 2, but here C is factor 1. Okay, so this is the optimized condition. What you can say, for A it is factor 2, this one. For B it is also factor 2, C is factor 1, not factor 1, this level. For A it is level 2, for factor B it is also level 2, for factor C it is upward towards 1, so level 1. Factor D, it is level 2 because in factor D it is going towards 2. So like this is the optimized condition, is an optimized setting. Okay, now next is we'll have to fit the linear model. Okay, to fit the linear model, first of all you will have to fit the design of experiment of the Taguchi that you have made using the LM function of the R. I'll show it now. Thereafter you will have to carry out the ANOVA, okay, to see which factors are having the significant influence. Then you will have to predict the yield using this model, because this linear regression will generate a model. So from that you will have to predict the yield. Okay, and then lastly you will have to verify experimentally, because the yield which is predicted by this model, you will have to use the same condition and do the experiment once again and see if the predicted yield is similar to the experimental yield. I'll show it now. So we go back to the R software. Okay, okay, here one more thing I forgot to tell. This is the signal to noise ratio plot. So one more plot is there. This is called effect plot. So effect plot also you can see using the, yeah, so this is the effect plot. Okay, I'm not going detail because the signal to noise ratio plot is more important than effect plot. Okay, now next is we go to the Excel sheet. So in the Excel sheet, now we go for the linear regression. So for this, just copy the whole table once again. Just copy it and thereafter come here. Okay, so now I'm naming this table as a design. So I just run it, and after running it, structure is not important, but still we can see the structure of the design. So you can see everything is integer and number. It is not very important. Now we are to go for fitting the so here we are using the LM function, and here y. if you go to the Excel sheet, what you can see is the y is the response. So we put y over here, and then this sign is put, okay, for regression. Then a is the first factor plus b plus c plus d plus e plus f plus g. Okay, we put all these things here, and then we write data is equal to design, because we have named our data as design. And then we run it. After running, the next is we'll have to go for the ANOVA. We click run here. So this is the ANOVA. So what you can see is that the factor A, the p value is less than 0.05, factor B also 0.05, less than 0.05, and factor D also. But what you can see is that the C, it is C, then E, F and G. So these factors, they do not have significant influence, but factor A, factor B and factor E, these things, they have got significant influence. That is evident from the ANOVA. Okay, now what we do, we just, next is summary. So in the summary command, we'll show the summary of the regression that we have done. So what you can, this is the summary of the regression. So here what you see is that the R-square value, the R-square value is 0.95, that is 95%. So it is a good fit, and the regression is good. And now the next is we have to go for prediction. Okay, so for prediction, we use this predict, then linear fit, name of the vector for the regression, then data.frame, and a is equal to 2. If you remember, so this was our optimized setting. So a is equal to 2, b is equal to 2, c is equal to 1. So same thing we'll have to write in the predict function. So here under the data frame, a is equal to 2, then b is equal to 2, then c is equal to 1, then d is equal to 2, e is equal to 1. So like this to write, and then we do it here and we click run. So after clicking run, what you see is that the predicted yield is 70.24. So what it indicates is that once we do the prediction using this particular setting, okay, so predicted yield is 70.24. That means if we use this, this particular setting, so what will happen, the yield that is predicted is 70.24. Next is the experimental validation. So now you carry out the experiment once again, but this time you take only this particular setting. That means in the factor A, you choose only level 2, not level 1. So B also you choose level 2, C also you choose level 1, like this. In this setting, you carry out the experiment. Okay, now supposing that we have carried out the experiment, and this is the experimental values. So this is the predicted value that I have shown earlier, 70.24, and this is the experimental value. So 4 values I have got, because I have conducted this experiment in 4 replicates. 4 times I have done the experiment, and I've got 4 values. So the mean value is 70.375. It is almost equal to that of the predicted value. But in order to, because I cannot say that it is approximately equal to this predicted value, so it should be accepted. I'll have to show this statistically. So for this, we are to carry out the one sample t-test. So one sample t-test, if this value is similar to this value, so the p-value will be more than 0.05. So we go to the R software, and here, so I have entered the value 71, 71.5, 16 and 70. So these are the experimental values I have obtained. So let me run this code. Okay, now I go for the t-test. So the t-test, mu is equal to 70.24. That to be removed. So the mu is equal to 70.24. This 70.24, it is a predicted value, and the x is the vector where I have entered the experimental values. Now I carry out the one sample t-test. So this is the result of the one sample t-test. What you can see is that here the p-value is more than 0.05. So this indicates that the experimental
values are not different from the predicted value. So this condition can be taken as a optimized condition. Thank you for your patient hearing. If you have any question, please write your question in the comment section. Thank you very much.